Hi, I'm Brock. Going to be talking about stateful aggregations and structured streaming and how you can connect Scylla as either a way to store your state or a way to store your results with Apache Spark.
Hello, everyone. Great to be here. Today I want to explain to all of you all the cool stuff that you can do with structured streaming regarding streaming aggregations and stateful aggregations. So who am I? First of all, I'm a software engineer at Databricks. I work in the streaming team, so our motto is we make our streams come true. I'm a Apache Spark committer since February 2017 and did my master's in management science, did my bachelor's in mechanical engineering. I'm not a database person, but coming out from a different angle, it's very cool to see how we can do all this stuff. So about Databricks, the team started the Apache Spark project back in Berkeley in 2009. Our mission is to make big data simple, and our product is a unified analytics platform, which I'm going to do a demo on later in the presentation. So today, I have a very quick outline. I just want to explain to you, first of all, some concepts around structured streaming. Then I'm going to explain a little about stateful processing and structured streaming. Then I'm going to talk about some use cases and how NoSQL stores can fit into these use cases. And with the power of Spark, how can you fit all these tools in there to build end-to-end beautiful applications? And then I'm going to do some demos. But before I start, could I please get a raise of hands of who has ever heard of structured streaming before? OK, several people. So I'll try to explain the concepts in a little more detail. So basically, with structured streaming, what we wanted to talk about was, it's very hard to do streaming analytics. There are like a lot of cases that you have to keep in mind, and it's very hard to reason about. Basically, when you have a batch mindset and then you want to go into low latency world. But what we said was, with structured streaming, you don't have to, like when you want to deal with streaming analytics, maybe the best way to do it is not to reason about streaming at all. Just think of it all as infinite tables. So you have a table coming in. You have a data stream coming in. What you do is, as your data stream comes in, you append it to an unbounded table. And basically, new data in the stream is new rows appended to your table. So with our new model, we have like several concepts. The first is your input data. So where's your input coming from? It could be log files. It could be Apache Kafka. It could be a table on a MySQL table. It could be a Cassandra or a Scylla table. So you have new data coming in here, and it has to be an append-only source. So then you have a trigger concept. What's your trigger? The trigger is basically how often you want to look if new data has arrived. And when you look if new data has arrived, you emit results. Then you have your query, which is basically what you all are aware of, all the operations that you want to do on your data. You have the concept of a result. Basically, as you perform your transformations, you write it out to some result table. And this result table is updated every trigger interval. And then you have your output mode, basically, which says, what part of the result table do I want to output to a sink? So a streaming sink is where you eventually store your final data. So one of the output modes is complete output mode, which is the simplest to reason about. It's basically, if you had all your data available, and you ran a batch job on it, this is the result you would get. So forget about streaming. You have your input data. You run a batch job. And then complete output mode gives you the same result in streaming mode as well as in batch mode. So you output all the rows of the result table to your sink every single time. When you have append output mode, basically this is all the new additions to your result table get outputted to your sink at every trigger interval. So a very simple example here of word count, streaming word count. you have your data coming in across time. So you have your lines of data coming in, like cat, dog, dog, dog. You do your group by, you tokenize, and then do a group by count, and then your cat dogs are outputted to your sink. When you get new data, you output all the rows again in complete mode. You get more data, you again output all the data. So if you had all of this coming in at a single event, the complete mode would give you the same output. So a little into more detail, because this is where like a lot of complexity comes around aggregations. So basically, append mode means that when I output this row out of my data, I cannot change it ever again. This is the final result. So what this means is that if you're doing like aggregations and you're doing like windowed aggregations, you can't output the row as soon as you just get the first record for it. You need to wait until the window completes, and then you need to account for late data. And then once you're sure that you're not going to get any more data for that row, you can finally output the result for that window. And the example use case here is ETL. Append mode is the default mode. So basically, if you're doing aggregations, you can only output once your result is guaranteed not to change. Or if you're just doing map-only transformations, you'll use append mode. Complete mode, like I said, this is basically outputting everything to your sink after every trigger. This is currently supported for aggregation queries. You can't do this for like ETL cases, because that just means you have to save all the data in memory and output to your ETL output table every single trigger, which is infeasible. So aggregation queries, we assume that you'll have some bounded data, so you can output this data every single time. And an example use case for this is monitoring. Update mode is, I assume you'll all be familiar with this. You have a primary key, your results change, you update the result for that primary key every trigger. It's basically an append mode kind of style where you can output partial results as you go along, because the sink knows that, okay, I need to change the value for this primary key. And you can use this for like alerting or like sessionization use cases. So, very high overview. Let's go into stateful processing and structure streaming. So one of the things that we wanted to make a first-class citizen in structure streaming was event time aggregation. It's basically when people do aggregations, they don't generally care about the processing time. We've seen that people actually care about the event time of their data. And when we were working on D-streams, we didn't have this kind of support. The only support we had was processing time. So with structure streaming, we wanted to make event time aggregations a first-class citizen, and then we saw that there are many challenges regarding handling event time data, whereas you can get out-of-order data, you can get late data coming in, someone's phone is off the Wi-Fi and it sends data 5 minutes later. So you get all these like out-of-order, late data coming in, and you need to be able to reason about that. But what we wanted with structure streaming is you don't need to care about that. You just care about your business logic. We'll just handle all of the complexities for you. So for example, windowing on your event time is basically just another type of grouping in your structure streaming application. It's very simple. You want to do a group by aggregation. You can go and select your window and of timestamp 1 hour, for example, and then do a count of all the records that you received in that 1 hour. Or if you wanted to group by, like your device ID, for example, you can just add it as a separate column in your group by query. And you use built-in functions to extract event time from your records. Therefore, you don't need any separate extractors, which is a common complexity in like other streaming systems. And it's basically in your data and do whatever you want with it. You can change timestamps, you can change time zones. It's totally up to you. And you have the power of Spark and all the built-in functions helping you do these things. If you want to do advanced aggregations, we have a lot of powerful built-in aggregations. For example, if you want to do a lot of statistics around variance, standard deviation, correlations, collecting lists or sets of your data, you can do all these very easily. Spark already supports these natively. And the beauty is you can do simultaneous aggregations in one of your query. You can calculate basically the average, the standard deviation. You can calculate the maximum. You can run like approximate quantiles and get several quantiles of your data in a single query very efficiently. And if you want, you can go crazy and write your custom aggregation functions, declare UDAFs, and then write them in your Scala code, Scala Java code. So let me talk about stateful processing for aggregations. Basically, by default, Spark supports an in-memory streaming state maintained for aggregations. This in-memory state allows late data to come in and update the count of old windows. But the thing you have to be careful about is that you want to be able to get rid of this state unless your state will grow unboundedly. So, for example, here in our example, you can see late data being updated on the blue rows, and you will eventually, in append mode, evict state as you go along. So let me talk about the in-memory state, for example. If you're thinking in-memory, how is this fault tolerant, right? What if the node crashes? Well, basically, to make sure we have a fault-tolerant system, we use a write-ahead log to save the state in between each trigger. And this write-ahead log allows us to recreate the state at any moment in time. This way, you can get fault-tolerant exactly once stateful processing semantics with structured streaming. And handling late data and bounding your state is another question. So for that, we have the concept of watermarks. And watermark is basically a moving threshold that trails behind your max event time. And you define basically a delay of how, as you own your system, you say, okay, my data will arrive at most 15 minutes late. So you define how big the trailing gap should be. So what this means is data older than the watermark is not expected. And if we do receive it, we're just going to discard it for our aggregations. If you have late data coming in, but it's before the watermark, we'll keep updating the state for that watermark, state for that key. And basically, what you want to control here with your delay is that you want to control the trade-off between how much state you keep in memory and your latency requirements. If you set the watermark to be too high, for example, a day, and your structured streaming application uses append mode output, that means that you're not going to see your results for a whole day. If you say it's like 15 minutes, then append mode output can produce the results for you in 15 minutes, but then you might not handle late data that came like a day late. And you specify the watermark on your column with the with watermark function, the timestamp and your delay key. So moving off of an example, you can see how our data is coming in. We have data coming in at like 12:07, 12:08, and then as new data comes in 12:14, the max event time is tracked. And then we provide the delay key to set our watermark. And then once you receive a record at like 12:15, you have a 10-minute delay, so our watermark's at 12:04. The data that's like at 12:08 that arrived at like 1217, basically, will be included in your aggregation. But this data point, which said was 1203 or 1202, this guy will be discarded. And there, we have a blog post explaining all of this in a lot more detail if you're interested in the databricks.com blog website. So another example, on the cat-dog example, you have your data coming in. You have your cat, dog, dog, dog. You have your counts. And then you have your dog record that came very late at like 12:11. But the event time of that record corresponds to 12:04. You can still update the aggregation and your windowed state. So to summarize, working with time, what we wanted to do was separate the processing details from your query semantics. And basically, when you do a window, you specify how to group your data by time. We also support sliding windows. It's just another more record here. So this is a tumbling window of 1 minute. Then you're saying, my data can arrive at most 5 hours late, when you say your watermarks delay is 5 hours. Then you say, trigger output for me every 10 seconds. So this is how often to emit updates. So with Spark 2.2, we added the support for arbitrary stateful operations. What do I mean by that? You can write any business logic that you have in a function called MapGroups WithState. And what this does is basically you give us a grouping key. And for this grouping key, we will give you the list of the values received for that key. And then with this, you can do whatever you want. And in my example, I'm going to show you an alerting example using MapGroups WithState. So you take the key, you have your in-memory state, group state, which you can use, and then you have your iterator of values received for that key. You can use timeouts, because there could be cases when you're doing like sessionization, for example, that you don't receive data for a given key. That means your session might have timed out. And for timeouts, you can use both processing time timeouts or event time timeouts. So processing time you might want to do if you have a very, it doesn't matter that data isn't arriving. You just want to make sure that data is definitely arriving for some key. And if it's not, all hell breaks loose. So you can use processing time. Or if you want to keep your logic around your event time, you can use event time timeouts. So flat MapGroups WithState is a generalization of MapGroups WithState. It applies the given function to a group of data while maintaining a per group state. It is invoked once per group, per batch, and it's invoked each trigger with the existence of data per group in streaming. If your function has timed out, for example, then it'll still be evaluated, but your input data will be empty. And flat MapGroups WithState requires the user to provide an output mode for the function. So here, let me explain this in more detail. MapGroups WithState is a special case of flat MapGroups WithState with an output mode of update and an output size of 1 row per group. With flat MapGroups WithState, you can output an arbitrary number of records, each trigger. And it could be 0, it could be 10 records. And your output function defines how we should handle this in our result table. So if you're outputting 10 records in update mode, that means our primary key will have like an array of 10 records. And it's going to replace the array of 3 records that we received before. Or if it's append mode, basically, we're just continuously sending new records downstream to our query. And flat MapGroups WithState also supports both processing time and event time timeouts. So some use cases and how NoSQL stores fit in to these use cases. For example, a very nice alerting use case. You want to monitor a stream using some stateful logic with timeouts. Let's say our stream has events. We want to group by the ID of the event. And then we can use flat MapGroups WithState in append mode, for example, with a processing time timeout. And you can put in any logic you want in here. And then you can write your stream using a for each writer to, for example, PagerDuty. You can send PagerDuty alerts using RESTful APIs by the output of your stateful logic. How can you use NoSQL stores here? Basically, you can save your state to Scylla to power dashboards in the meantime. So you can have your dashboards keeping the state, and your logic outputs some results based on this state and makes alerts, and have the stream trigger alerts ASAP. Or you could have, like a sessionization use case where you analyze the sessions of user system behavior. And here you might want to do event time timeout, just so that, basically data to account for arrival of late data. And then you could write it out to Scylla or Cassandra. And this could power other dashboards, or it could be used by any other downstream application that you can think of. So your output could be saved to Scylla or Cassandra or wherever as well. So I would like to do a quick demo showing some alerting use case on structured streaming and Databricks. Let me zoom in. So what we want to do, we're going to alert on anomalies. So we're receiving data from sensors spread all across the US, and we want to detect sensors that start to act out of the ordinary. Our data is coming through Apache Kafka. We love Kafka at Databricks, and Spark has first-class support for Kafka. And our goal is to detect regional issues, and the way we're going to do it is as follows. So we're going to track the summary statistics of our sensors. We're going to track statistics like the count of acts received by the sensor, the sum of the values received by the sensor, and the sum of the square of the values received by the sensor, so that we can get a Gaussian distribution. From this Gaussian distribution, we're just going to say, okay, any value that's out of this 99.7% confidence interval, 3 sigma confidence interval, we're going to consider that anomalous. And then we're going to window these anomalous readings by 5 seconds of our event time. And we're going to count how many sensors behaved abnormally in a 5-second window across our region. The way I want to do, like 5-second aggregation plus per region aggregation is just to smoothen out individual sensors that could be malfunctioning. We want to know if something really bad is happening for a region. And we're going to show how Scylla can be used as a durable state store and a streaming sink. So let's start off by reading our data off of Kafka. We have our data set. It's called sensor data. It has a timestamp, our event time. It has a sensor ID. It has a region, which is a string. It has a zip code, and it has a value for the sensor. So in this example, we're going to use Scylla as a state store, and our output data is going to power a dashboard. So as I run this, we're reading data off of Kafka. We're grouping our sensors by their region. And then what we're doing is we're writing a flat MapGroups WithState function in append output mode with no timeouts. And what it's doing is it's filtering anomalous sensor data. This could be any logic you want. This could be your machine learning model that you've trained in Spark submitting predictions. But right now, like I said, it's just a Gaussian distribution filtering. Then what we're going to do is we're going to select the window start time of our timestamp with 5 seconds. And our region, we're going to group by the start and region, and we're going to do a count. So right now, I don't have any data coming in, because I'm going to push my data momentarily. And I'm going to start a second stream that does the exact same thing, but outputs the data to Scylla, to a key space sensors, a table called spikes, and I set my primary key to be the region and the window start time as well. And our output mode for this stream is update mode, whereas for the first stream, our output mode is complete mode. All right, so let's start pushing some sensor data into our Kafka stream, and let's see what happens. So we're starting to process 14,000 records per second, have all the power of Spark with structured streaming, but our output dashboard says everything's okay. There's no data coming in. We don't have any anomalous sensors right now. Let's see what the table in Scylla says. It should say the same thing. It should basically say, okay, there's no data because nothing's anomalous right now. So let's look at our state. So let's read our state from Scylla. As you can see, it has the value. It has the counts, the sums, and the sum squares. And what I'm going to do is I'm going to use a SQL statement to look at the means, the standard deviations, and the values for each region. And you can see, all right, like all the regions, they have a nice average. They're not the same, but they're in a separate. They're pretty stable, right? Their standard deviations are pretty small. Let's start pushing some anomalous data, and let's see what happens. Whoa, we now have data in our output, updating our dashboard in real time. And you can see how, like California is spiking, you can see how Colorado is spiking, and Nevada is spiking at the same time. So what does Scylla say? Let's see if our second stream is keeping up. It is. It's basically the same amount of showing the same values for our data. And we can look at the state now to see what it has turned to. And you can see California, Colorado, Nevada, it start to have higher standard deviations, and the average is still slightly increasing over time as I run it. All right. So Databricks, we have Community Edition. It's free to try out. Try Spark 2.2 and structured streaming on Databricks today, and you can try all this cool stuff. And if you want to learn more about structured streaming, we have on our Databricks blog, we have an anthology of structured streaming blog posts. We have a series of blog posts of scalable data at Databricks, of how we use structured streaming ourselves and track, and basically dog food what we build on real data at real scale, terabytes of data analyzed per day with structured streaming. And shameless career post, we are hiring. I'm lucky to have my face on the hiring page, but it's basically, we are hiring. So if you're interested and want to work on cool stuff like this, we'd love to have you. So thank you so much.